Well, I'm honored to start off this presentation. And once again, I want to thank you guys for putting this together in order so we can showcase our work. So let me start off with the first slide. My objective with my studies was to compare model forecasts of total water level to observations. I wanted to identify model scale based on wind speed and wind direction, and ultimately create an easy to use tool for our forecasters to use when they are forecasting total water level in the eastern North Carolina region. So you might be asking yourself, well, what is total water level? So essentially it's the sum of your astronomical tide, a base tide anomaly, which essentially is an adjustment factor that accounts for multiple biases, in addition to storm surge, which is defined as the instantaneous wind affected difference in tide. The value of total water level is that it answers the need for actionable coastal water level forecasts. So rather than just making a forecast for storm surge or just a forecast of tide, it's how much water should I be expecting as a property owner, or etc. So the area that I was focused on was eastern North Carolina. Moving north to south, we have Duck Pier, Organ Inlet, Hatteras, and Beaufort. The reason that we chose these locations was because of data availability, along with a diverse coastline. You could see that depending on which way the wind's blowing at any given time, water is going to move into that area and bulge up in that area. And the Pamlico Sound is one thing that makes this this region very unique. It has a lot of water in its CWA, and that makes total water level forecasting important. So in 2018, Brandon Black, he was a volunteer that did similar research of total water level, compared forecasts of 10 high impact events versus actual observations. And these forecasts came from the forecaster, so not the models. This was what the forecaster actually was forecasting. What he found was that Duck and Organ Inlet, there was a slight tendency to over forecast versus Hatteras and Beaufort. And so what I was really focused on was how do the models perform when forecasting total water level. And so there's three models that are used to forecast TWL. That's the ETSS, the PETS, and your SDOFs. One of the major differences here is the SDOFs runs off the surge model called the ADCIRC, and the PETS is an ensemble model, while the ETSS is just one deterministic model. So talk a little bit about the data before we jump into the results here. I was able to use Python for a majority of this project. All the data came from NCEP. Thanks to them for supplying the data. The observations came from the National Data Buoy Center archives. And some of the differences here is that the date ranges for the ETSS and PETS was from 2017 to 2020, while the SDOFs was from 2018 to 2020, March of 2020 that is for both. And I want to point out a datum. So what a datum is essentially it's where do you start to measure from. There's different sort of datums that we use along the Atlantic coast. However, mean lower low water is the what is used for observations, and so we wanted to do the same with our model data. What mean lower low water is say there's 2 low tides a day, it's the average of the lower one every day over a 19-year period. So it's important to establish that datum so that you know everything's on a level playing field from what you're measuring from. And as for the forecast periods, so there's 4 different, each model is run 4 times a day. And what I was focused on was the 24-hour forecast, the 48-hour forecast, and the 72-hour forecast. So for each model run, we're taking essentially 3 timestamps of data, and we're compiling that all into Python to do the analysis. So once again, I want to emphasize the importance of bias in a total water level calculation. So biases exist in storm surge models. They can range from sea level rise to wave impacts, river discharge, and rain, and including a bunch of other anomalies as well. Now, so to counter these effects, the ETSS and the PETS add a 5-day average bias to the total water level calculation in a station-based post-processing stage. And on the right side here, you can see the equations that are used to calculate that. So I want to emphasize the SDOFs model is not, or the output is not a total water level guidance. Actual water levels can be significantly higher than forecast due to biases not presently included in the SDOFs. So the SDOFs model was able to forecast for tide and storm surge, but it does not have that bias factored in. So I needed to essentially create a bias and add it to what the SDOS was outputting in order to compare apples to apples. So now let's get into some of the results here. What you're looking at, this map, on the x-axis, you have wind direction in degrees. The parenthesis means that it's not included, and the bracket is that it is included from a degree standpoint. The y-axis, you have percent error, and the colors here, green represents the ETSS, orange represents the PETs, and pink represents the SDOFs. There's two important statistics that I want to highlight. The 50% error represents the median, while the IQR is the interquartile range, which is quartile 3 minus quartile 1. The importance of these is the median is going to give you a sense of whether or not you're going to be over forecasting or under forecasting, while the IQR is going to show variability. The smaller the IQR, the lesser the variability, the more consistent that model is able to forecast. So if we're looking at here, you can see the ETSS and the PETs are around the low 20s from a IQR standpoint, while the SDOF is a little bit higher for duck, and all three models tend to under forecast slightly. For Oregon Inlet, you have an IQR in the low 40s for the ETSS and PETs, while the SDOS is in the upper 30s. Again, all three models tend to under forecast. What's pretty cool here is you can actually, based off wind direction, you can see all three of the models tend to over forecast when you have a northerly wind direction and actually under forecast when you have a southerly wind direction. For Hatteras, you can see the ETSS and the PETs in the mid to low 40s from an IQR, SDOF a little bit higher, coming into the mid 50s, while the SDOF tends to under forecast for Hatteras, and the ETSS and PETs tend to over forecast slightly. And now for Beaufort, you can see the ETSS and PETs are coming in the low 20s for IQR compared to low 30s for the SDOFs, and all three models tend to under forecast. So overall locational performance, you can see, and this was essentially an ensemble of all three models per each location to get a gauge of, do the models have a better handle at one spot versus the other? Duck and Beaufort came in with an IQR in the low 20s compared to Oregon Inlet and Hatteras, which were in the mid to upper 40s. So I would say the models have a better handle with Duck and Beaufort compared to Oregon Inlet and Hatteras. One of the reasons that I think this could be happening is because the amount of water that is able to be pushed in Oregon Inlet and Hatteras is more compared to Beaufort and Duck. If you look in the top right here, there's a lot more water available to be pushed into those locations. And from a median perspective, all four locations besides Hatteras tends to over forecast just slightly compared to the other three. And below here you can see just the wind rows of observational wind data, the frequency of wind speed and wind direction for each location. Now the overall model performance, removing location and just looking at the models, ETSS and PETs, very similar with their IQR in the low 30s, SDOF's a little bit higher in 38. Now, I want to talk into more about the tool that I was able to create for forecasters to use, sort of a process that I was able to compile here. If you're forecasting for a location, you could look at these broader scale maps per location and identify which model performs the best overall. From there, you can go to the search tool that I was able to create, which goes into much more detail of wind speed, forecast period, and wind direction, which I will show you next. And then from there, you can make an adjustment as a forecaster based on sample size and your confidence. So here's the tool I was able to create. There's going to be an example. Let's say you think the winds are going to be out of the south from 11 to 18 miles per hour, gusts as high as 24. So I'm going to, hopefully this works, or it should work. I've tested it many times. So let's say, let's go to Oregon Inlet. So we have all four locations here. Let's say it's a day one forecast, and let's take a look at 10 to 15 knots. So on the right, you have your wind rows for that specific, how many, or whenever the observations of winds were between 10 to 15 knots, it's going to show your frequency of wind speed and wind direction on the right. And on the left here, in more detail, you can see, okay, if we think the winds are out of the south, let's look between 150 degrees and 210 degrees. We tend to under forecast here from, if I had to say, 7 to 15%. So if I'm a forecaster, I might want to bump up, whatever the models are saying, bump it up slightly. Now we could take a look at the PETSS as well. It's a little bit more. So from -10 to -20% here. So we might want to take that into consideration as well. We have that for the SDOFs as well. And we have, so that's a 24-hour forecast. We have 48-hour forecast and a 72-hour forecast. And that's for all four locations. So pretty cool tool that we were able to create and hopefully help improve total water level forecasting. Coming to a close here. So I want to re-emphasize from a model functionality standpoint that ETSS and the SDOFs, they both calculate surge values, they both calculate tide values. However, when it comes to total water level values, the ETSS and PETS does forecast for that, while the SDOFs does not forecast, because the SDOFs does not include a bias. So if you are using the SDOFs as a forecaster, you can use the percent errors from that tool to adjust, let's say, your surge values or say your tide values. But I just want to emphasize the SDOFs model does not calculate total water level as of yet. So in conclusion, the ETSS and the PETS have very similar output given to the short range forecast and the fact they're both run on the same surge model. Models tend to under forecast for Duck in Organ Inlet and Beaufort, while slightly over forecasting for Hatteras. Duck and Beaufort have less forecast variability compared to Organ Inlet and Hatteras. There's slightly more variability from day 1 to day 3 in the models, but not by much. As wind speed increases, the model's percent error variability increases. But once again, it's important to keep into consideration that sample size. If you're looking at events where winds are gusting over 20 knots or winds are sustained over 20 knots, you might have a little bit less confidence because there's not as much data there. And the ETSS and PETS overall performs better than the SDOFs. So once again, I want to thank everybody from the Hollings Scholarship Program, and especially everybody in the Newport Morehead City office, Ryan, Casey, Quinn, David, Bell, Shane, and Carl, for all your help. Without you guys, this would not be possible. So thank you guys for listening to my presentation, and I hope you enjoyed it.
Talk number 2, Liam Sheji from the University of Miami, hosted again here by us at NWS Newport Morehead City. He's going to do a talk on the analysis of radar signatures associated with tornado warm storm cells during hurricanes Florence, Dorian, and tropical storm Hermine in eastern North Carolina. Liam, take it away. The floor is yours.
Alrighty, thank you, Ryan, for the introduction. I'm going to share my screen now, and just want to make sure that you can see this all right before I start.
Yes, that looks good to us.
All right, perfect. So I'm going to go ahead and start. As Ryan said, my name is Liam Sheji. I'm a student at the University of Miami, go Canes. And I was hosted by the National Weather Service Newport Morehead City office, and I will be doing an analysis of radar signatures associated with tornado-warned storms during Hurricane Florence, Hermine, and Dorian. So starting off on some background, North Carolina is very prone to hurricanes and tropical systems throughout the year. The return for a hurricane on the North Carolina coast on the first image is 5 to 7 years, which is among the highest in the country. And one of the big things that comes with hurricanes is the chance for isolated tornadoes. So it's important to be able to forecast the area most likely to have isolated tornadoes ahead of a tropical cyclone. And it's also very important to be able to diagnose a supercell as tornadic as they approach. So previous studies aimed to determine which features and parameters will tell a forecaster the most about the likelihood of a supercell being tornadic. And I'll be looking at 2 things. I'll be looking at the environment, and I'll also be looking at individual cells and analyzing them from there. So starting off with the analysis of the environmental parameters, a paper by McCall in 1991 sets a good threshold for values that would signify a strong environment for tornado formation, and later papers also work to pick out which one of those parameters are the most influential, and those happen to be the surface-based CAPE, the 0 to 3 kilometer shear, and the 0 to 1 bulk storm relative helicity. It's also important to note that in a tropical webinar by Roger Edwards, who is an SPC expert, he explains that most tornadoes should fall in a downshear right quadrant relative to the shear vector from 850 millibars to 200 millibars, and strongly sheared would be considered greater than 20 knots. And into this analysis of the individual storm cells, I will be using the WDTB guidance, which has been renamed to WDTB, which is the Warning Decision Training Division. And they developed a guidance chart based on studies previously done that go into the steps of how to diagnose a tropical supercell. Now I'll be going individually through all those parameters and describing what they mean and how they show. So the methodology for this project, I used the Morehead City radar, and I was looking at Dorian, Florence, and Hermine. And of all those storms, 46 warnings were issued. 21 of those were verified, and 25 of those were non-verified. And then I looked at the SPC mesoscale analysis archives, the ship's model output, and the environmental soundings for the tropical environmental study around Morehead, North Carolina during the times where these hurricanes hit. And for the cell analysis, I'll be looking 5 volume scans prior to genesis, which is about 4 to 6 minutes for a volume scan. So that's about 30 minutes before the tornado touched down. And I'll be looking for 3 volume scans after, unverified, or until the warning time stopped for the verified cells. And each of the parameters are measured in GR2 analysts that are based on the WDTD guidance, and I'll be going through those later as well. And I hypothesize that Florence will have most of its cells in the downstream right quadrant, while Hermine has a weaker environment than the rest due to its low tornado output. And that one of the parameters, KDP-ZDR separation, may be more useful when adding a marginality onto that. And also that NROT, which is a tool that's not often used, will be a good verification tool. So going into the environmental study, McCall describes that most tornadoes should fall within the 0 to 120 degree mark relative to the tropical cyclone forward motion. However, that was not the case for all the cells. Most of the cells for Florence fell outside the 120 degree mark, which can be later explained by using the Edwards guidance as well. So starting with Hermine, the values for helicity, cape, and shear were all high as tornado production started around 0Z. The helicity approached 400 meters squared per second squared, and the offshore cape was around 1,000. And the 0 to 3 kilometer shear was under what guidance recommended. However, the shear vector was 35 knots from 850 to 200 millibars, signifying that's a really strong shear vector and that most of the cells should fall within the down shear right quadrant, which happens to be the case, all of them do. For Florence had a really small forward speed, so it lasted a while, and those parameters lasted for a while, leading to a lot more tornadoes touching down. And that's balanced by the fact that helicity and shear values were high as well, 500 for the helicity and approaching 1,000 for the shear. And even the 0 to 3 kilometer shear was very high. However, the bulk shear from 850 to 200 was 13 knots, which is lower than what's considered strong. But even regardless of that, most of the cells still ended up falling in the downshear right quadrant, with only 3 falling fully within the downshear left quadrant. This is a really important conclusion because it shows that maybe that the 0 to 120 degree mark isn't cutting it, and you should look at the shear vector instead. And this would be a really good tool for diagnosing ahead of a tropical cyclone whether a tornado would touch down or not. Moving into Dorian, the same kind of spiel. The values all fall in line at the time of formation. However, the 0 to 3 kilometer shear reaches its peak value at the time where tornadoes stop forming, and it decreases on from there, showing that maybe the 0 to 3 kilometer shear would have a greater impact, showing when tornado production will stop. And falling in line with Hurricane Hermine, all the cells fell into the downshear right quadrant as it was just barely strongly sheared. So going into the cell analysis individually, the first parameter that I'm looking at is the rotational velocity, and that is essentially a measure of the rotational speed of an individual cell. And per the guidance given, within 40 nautical miles of the radar, 20 plus knots is considered strong enough for a warning. From 40 to 70, 15 or greater knots is considered. For greater than 70 nautical miles, 12 greater knots are considered. So looking at an example from Hurricane Florence, this storm cell at the beginning of the analysis did not have a rotational couplet, but going into later volume scans, you can see it start to form. The values of red start to grow stronger as you go through, and so do the green values. By volume scan 1, you get a value of 40.8 knots, which is very strong, way higher than the 20 knots. By volume scan 0, it's even higher at 49.2 knots, signifying a very strong signature, which would be inducive of a tornado. So moving on to a tightening velocity couplet, essentially that's just how the diameter of that VROT changes over time. And that's typically only used for cells that are less than 40 nautical miles, because past 40 nautical miles, the radar width beam gets so large that the resolution isn't good enough to be able to discern accurately the diameter. So going through the volume scans, as I said, volume scan -4, which is shown as VS going into the future. There is no couplets and no diameters measured. Going through volume scan 3, that couplet starts to form and it has a value of 1.21 nautical miles. Going through, the diameter keeps tightening until it reaches 0.15, which is the smallest value that you can measure with diameter, since that's the closest the pixels can be to each other. By volume scan 0, that holds true, and that is a very strong couplet, therefore, since it's under 1 nautical mile. Going into a hook echo, this is probably the one that most people have heard of. It's basically a feature that's noticeable on radar that looks like a hook. And it shouldn't be used on its own to diagnose a tornado, so it's typically used in conjunction with the other methods that I'm going to be showing. So starting at volume scan 4, there's not really a clear hook defined, but you can really start to see that hook shape start to form as you go into volume scan 2 and 1, And then once you get to 0, that's a very defined hook. And at the end of the hook there, that blob, that is where the tornado is most likely to be. The next factor is the KDP-ZDR separation, which is 2 factors combined that show you 2 different things, but when they work together, they tell you a lot. So the differential reflectivity is shown as ZDR, and that tells you about the drop size by measuring the horizontal and vertical difference in drop size, while the specific differential phase, the KDP, is similar, but it also takes into account the shape and concentration. And when you outline those parameters and put them and overlay them on top of each other, it tells you about the size separation of the particles, which tells you about the strength of the mesocyclone you're looking at. So at volume scan -4, they're still not separated that well. Later volume scans show that as well. Volume scan 3 still not very separated when you overlay them on top of each other. But by volume scan -1, you can drive a clear line, a horizontal line through it and see that they're pretty clearly separated. And at volume scan 0, they're fully separated. It's very clear that this is a strong mesocyclone that has the ability to produce a tornado. However, this should only be used within 70 nautical miles of the radar and is not always found in tornadic supercells, so it's typically used in conjunction with the next factor, which is VES, or velocity enhancement signature. Typically, this is a 30 knot or greater velocity signature noted in the mid-levels of a mesocyclone. And at volume scan 4, they usually start to present, so you can see that at the 10.4 kilofeet, which is at 10,000 feet, you can see that the green values are much higher, which shows that this is a VES signature. And going through volume scans, you can see that start to increase and stay at around the same level until you get the volume scan -1, where it reaches its highest value at 7.8 knots. That is a very strong VES signature and is very conducive to the production of a tornado. And at volume scan 0, it decreases slightly, which is on par with what guidance has shown. The last thing I'm going to be looking at is the normalized rotation, or NROT. This isn't ascribed by the guidance that I used, but it's really good for finding areas of rotation. And but it could potentially add merit to forecasting the location. So significant values are considered greater than 0.8, which are very strong blue values. Going through the volume scans, it starts as a very dark blue at volume scan 4 and 3. Going through, you see those blue values start to increase and it becomes way brighter. And by the time of the tornado touching down, those values have reached over 1, which is very indicative of a strong tornado. So now that we've gone through all the parameters that we're looking at, I can start to describe what I found after analyzing all 46 cells and their features. So starting with the rotational velocity, whether it was verified or not, it did increase significantly over volume scans, reaching its max value at volume scan 0. And it's important to note that after volume scan 0, the frequency of cells that had couplets started to decrease significantly. So those later scans were not shown in the study. And there's also no obvious trend in the radar range because there's not just a small enough sample size greater than 70 or 40 nautical miles. So the sample size is too small to make a definite conclusion on that. However, going into the diameter, you can see, as according to guidance, it was also shown that the diameter decreases rapidly as you approach genesis time, and it does agree well with the 1 nautical mile given by the guidance, as after volume scan 0, it does typically say stay at 1 nautical mile greater plus or minus around 0.25 nautical miles for every supercell for verified and unverified. And it's also important to note that these values are skewed for the later volume scans, as for volume scan 5, 17% of them didn't have a couplet. In volume scan -4, 10% did not have a couplet. And by volume scan 3, the one that's not shown all the way on the right, only 25% did not have a couplet. So those values may be slightly skewed looking at them. Next is the frequency of the hook echo, and the most frequent time to be able to see those were around volume scan 3 to volume scan 0, which makes sense with the VROT calculations, as many cells did not have a couplet before then. 81% of the verified cells had a signature, and 80% of the non-verified cells had the signature. So that further proves that the hook echo should be used if you're on the fence and not used as a tell-all about the tornadicity of a supercell. Going into KDP-ZDR, even though the sample size for non-verified cells was higher, you can still see that there was little to no separation for the cells. And for verified cells, that separation is very clearly seen after volume scan -2. And 76% of the verified cells had this separation and 40% of them did not. For the VES signature, throughout the time scans, it remained rather constant and the spread remained rather large up until volume scan 0. And most of the supercells had a very weak VES signature. And by weak, I mean less than 40 knots. And the mean value for that was considered around 45 knots. And that also proves on the frequency of these values, as after 45 knots, the frequency of higher values decreases, which shows that 45 knots may be significant and trying to show a cell is tornadic or non-tornadic. 76% of these cells had a VES signature, and 32% of them did not, showing that VES is still a good parameter for diagnosing a supercell. And the last parameter I looked at was NROT. NROT had the highest time at tornadogenesis at volume scan 0. That was the highest value, and it stood around 0.9. And the spread between volume scan 0 for verified and non-verified was about the same. So it's kind of hard to discern whether or not it's a better indicator for verified versus non-verified cells. However, all right, thanks, Ryan. So what this shows, though, is that after 1.1 value for NROT, the frequency of those decreases significantly. So that shows that a higher value around, let's say 1, would be more significant than a value like 0.8, which was shown less than the most median value. So we can come to some conclusions from this, that the shear vector that I use, the 850 to 200 millibar shear vector, gives us a better verification for the location of tornadoes ahead of time, even though the parameters from McCall were still found. 75% of the verified cells for the guidance had a hook echo, and 81% for my results did. But compared to the non-verified cells, their results showed 42, and my results showed 80, showing that hook echo may not be as good as an indicator as previously thought and should not be used on its own. However, there was still merit in trying to discern whether or not a cell is supercellular or not. Going into the KDP-ZDR separation, the results for my non-verified are slightly lower than theirs, showing that KDP-ZDR separation may be a better indicator than previously thought and could be used more often than the mesocyclonic VES signature. And then for the VES signature, 85 for verified, 76 for non-verified. And those results remain about the same from what I found for the guidance. And I also found that NROT values may be good at verification tool for the timing and the location of a tornado, but not good to diagnose whether a cell is tornadic or non-tornadic. And a final conclusion that I came to was NROT values greater than 1 are more likely significant than lower values like 0.8. So that is the end. And I would like to thank the NOAA Hollings undergraduate scholarship program and every staff member from the Newport Morehead City office, Ryan, Carl, Shane, Casey, David, and Bell. And I'd also like to thank my friends and families for sticking by during this and supporting me through this process.
And our next speaker will be Chad Wiley. He's from Millersville University of Pennsylvania, hosted by NWS Boulder, Colorado. And he is doing probabilistic snow verification for Colorado. So we will turn it over to you, Chad. I will see you are unmuted. I don't see a camera. Do you have a camera?
I do. It worked yesterday.
There you go. There we go. There you are. All right. We see you. We see the presentation. If you want to throw that in presentation mode.
All right. See it good? Everything good?
Yes, sir. Go ahead. The floor is yours.
All right. Thank you so much for hosting me. I'm so happy to be able to present this research, even though we couldn't do it in person. I'm still grateful for the opportunity to do this research and really get to network with all of you. So like you said, I'm Chad Wiley. I'm from Millersville University in Pennsylvania. I'm a meteorology major with computer science minor, and I did my research out of NWS Boulder, Colorado, with my mentors being Paul Schlauter and Chad Gimistad. And my project is probabilistic snow verification for Colorado. So over this talk, I'll give you some objectives of this research, some background and motivation, the methodologies, results, summaries, and some next steps that probably can take to help better this research. So my research goes with the NOAA objective because North and North Central Colorado annual snowfall varies greatly across the region, and understanding biases from town to town will help lessen the travel impacts of snowfall, especially across the two main interstates across North and Northeast Colorado, being I-25 and I-70. And by better understanding these biases will help to create a better weather-ready nation within the state of Colorado. Some personal goals: I wanted to become more comfortable with working with large sets of data and help to build and apply verification statistics, and as well as build upon some programming skills I picked up over the past few years in applied real-world research. So some background, like I said, vast amounts of snowfall ranges from Colorado in the mountains from about 400 inches to about 30 inches in the plains to about 60 inches in the general Denver metropolitan area. So, like I said, 2 inches of snow can disrupt travel in these major interstates being I-25 and I-70, especially during rush hour, and identifying the biases will better prepare CDOT for snow removal in these towns. So some methodology is I used 10 stations ranging from the mountains to the plains using Kokoros, Coop, and Snowtel stations. I'd identified my snow events from September 1st to June 30th of 2019 to 2020 with 2 inches at multiple stations to be considered an event. From there, I looked at the snow probable forecast from 60 to 20 hours out. Now, snow probabilistic forecasts come from the National Weather Service Boulder. They run about every 12 hours from town to town, especially at these stations. From there, the information I gained from there, they were more like the forecasts, percentiles, and greater than 0 all the way up to 18 inches. From there, I broke the biases into 3 geographical subsets, being the mountainous, metropolitan, and plains. Going forward, the plain stations were Greeley and Crook, metropolitan being Stapleton, which is also Denver, Arvada, Castle Rock, and Fort Collins, and mountainous stations being Dillon, Tower, Evergreen, and Georgetown. The stars denoting some major interstates running through these stations being I-70, I-25, and other state routes. So looking at the 36-hour lead times in the plains, Greeley looks pretty nice, a nice normal distribution, and nothing too notable, just looks pretty spot on for those forecasts from 36 hours out. As for Crook, a little different. It looks like there's more over forecasting, with the mean error being about 2.15 inches. And as you can see, there's a nice skew right on this, indicating that there's a over prediction of snowfall amounts. The same can be said for about 24 hours out, with Greeley becoming a little more accurate, as well as Crook, but as you can see, there's still the 5 percentile having a large skew in it. More of the same story for about 12 hours out lead time. Greeley almost being completely spot on the 50th percentile and almost 0 inches in error. And Crook again showing more skewed right with over prediction and snowfall amounts. Moving on to metropolitan area, 36-hour lead time. Denver Stapleton looking very nice with only about a ½ an inch of under prediction. Moving on to Arvada, this one we notice a large skew to under prediction, noting that 75, 90, and 95 were all significant figures in this, and as well as a mean error of about 2 1/3 under prediction. Moving on to Castle Rock, we notice that it's pretty similar, not similar, it's pretty normal distribution. Not much to say about this, it's usually spot on. As for Fort Collins, now there is some over and under prediction, some variability, and as well as an outlier. It is usually pretty spot on, and as it gets closer, as in the 24 hours, you can see that it becomes more accurate. Denver Stapleton, again, nothing much to say. It's normal. It looks like it's pretty accurate. No bias is found there. Arvada, you can see usually it's either on or it's very low under it, being that 95th percentile has a large amount. And you can see that there's negative 2.2 and a 25% negative percent error. Moving on to Castle Rock, you can see that there's a slight over prediction, being that there's a high percentile of the 5th and 25th percentile. They're not shown in the mean error or mean percent error due to some high outliers in the 100%, 150s. Moving on to Fort Collins, again, like I said before, it's pretty spot on. As for 12 hours, as I said before, metropolitan, it gets more and more accurate as 12 hours, as you move 12 hours closer to each. For Denver Stapleton, pretty spot on. Like I said, they've been pretty consistent this whole time, from 36 to 12 hours out. Arvada again showing, while it does get more accurate, there is a slight left skew with the bias being under prediction. Castle Rock shows more of a normal distribution with 12 hours and a pretty good percent error and mean error. And again, for Fort Collins, it shows that there's a slight under prediction, but overall it's pretty good. Moving on to the mountainous tower. This is in high in the mountains near Steamboat, Colorado, if you're familiar with that. So snowfall can be, it can range from a foot all the way up to about 3-4 feet. So here, there's a lot of times where there was over prediction, where the storm missed it, or there was just severe over prediction, which happened from time to time. For Dillon, it shows a skew towards under prediction, with the 50, the 75, and 95th all being about the same. Moving on to Georgetown, is a slight under bias, with 75, 90, and 95 being a large percentage, as well as the third percentile being pretty large in this case. Evergreen is a slight over prediction, with a large percentage coming between the 5, 25, and 50th percentile. Again, within 24-hour lead time, you can see that the 5th percentile is also very dominant in tower, showing that an over prediction. For Dillon, showing an over prediction, an under prediction with the 75th and 95th percentile, and Georgetown tending to be a more normal average distribution as you get closer to the storm. As for Evergreen, more of the same, just a few where there was some over and under prediction. Looking at the 12-hour, you can see the tower having 3 outliers that really ramps up the 5th percentile, showing that there's this clear over prediction bias in it. Dillon showing a right skew, again, with under prediction. Georgetown, normal bias, this looks pretty well, as well as Evergreen showing a skew to the right with over prediction. So in summary, it's encouraging to see forecasts become more and more accurate as lead time shorten. Tower, Evergreen, and Crook all show bias of over prediction for snowfall amounts, and Arvada being an under prediction of snowfall amounts, and not a clear noticeable bias for the 6 remaining stations as they all varied. And the ability to incorporate these trends into a forecaster's weather prediction or snowfall prediction can help the goal of having a weather-ready nation. So some next steps, I would also like to investigate the 2017 and 2018 seasons to see if this trend continues, and to also see why some places had a large over prediction or under prediction, being upsloping, convective, or there may be some common link between certain storms that causes these. So with that, I would like to thank Paul Schattler and Chad Gimmestad for mentoring me through this project, and as well as the NOAA Ernest team, Hollings team, for sponsoring this internship, and as well as anyone at the National Weather Service Boulder, or even some people at Millersville for joining this. Thank you. I'll take any questions.
We have Zoe Douglas from the University of Oklahoma, hosted by NWS Boulder, Colorado, doing radar detection of severe hail in Colorado. We'll toss the screen to you.
Hi, can you see me?
See you, can hear you well. You should be getting a pop-up to get your screen.
Yes, I'm just setting up my screen. All right.
There you are, it looks good to us.
Oh boy.
You are ready to go, the floor is...
Okay, can you see my screen?
Yes.
Okay, because I wasn't sure if the little pop-up from the GoToWebinar was showing at the same time. But it seems to skip ahead a couple slides. But my project this summer was with the National Weather Service office in Boulder, Colorado. So I would have been working with Chad Wiley, but we're all home instead. So it worked out. But my project this year is the radar detection of severe hail in Colorado. And once again, as Ryan pointed out, I am Zoe Douglas from the University of Oklahoma. I'm a meteorology major. And my mentors for this summer were Paul Schlatter and Robert Kalela. So same as what Chad had on his PowerPoint, I also have an outline just for the objectives, of this project, including NOAA's objectives and my own. There's a background for it, the methodology for what I was doing, the results, summary, and next steps for a project to continue next summer with a different Hollings scholar, and then the acknowledgements. So for this project, the National Weather Service in Boulder wanted to analyze very large hail events across northeastern Colorado in terms of both conventional and dual polarization data from radar and atmospheric soundings. Personally, I wanted to explore my deep interest in radar since I've had a little bit of a taste of it at the University of Oklahoma, but I do want to learn more. And I'm very interested in hail. Since growing up in the Midwest, I've really only ever seen like quarter-sized hail, so I could not imagine seeing 4-inch diameter hail. Like, that's wild to me. But I also wanted to do this project to prepare myself for grad school and ultimately a career in meteorological research. So the hypothesis for this project is that some of the parameters we were looking at from the atmospheric soundings and the radar data would be more useful than others, and that turned out to be true. So previous studies have analyzed these parameters across the entire United States, not just Colorado. They have found useful radar signatures for a very large hail, and the most significant one would be at the maximum height of 50 dBz echoes. So that depends on like how the higher it is, typically that indicates the stronger the updraft within a storm. And the other two important ones that were found in previous research would be a near zero differential reflectivity, or ZDR, and a reduced correlation coefficient. So for this project, I analyzed 88 very large hail cases, and in this project, very large hail was greater than or equal to 2.5 inches in diameter. This was all over northeast Colorado. I think I began with, 134 cases, but had a limit some because there was issues with the radar and the report times matching up, or there was just duplicates. So in total, there were 22 parameters between the atmospheric soundings and the radar. So for like atmospheric soundings, I was looking at like convective available potential energy, or CAPE, the Bulk-Richardson number, the wind speed and direction and temperature at 500 millibars. I was looking at all of that. And then for radar data, I was looking at the heights of the 50 dBz, 60 and 70 echoes, and then stuff like mesh and Ville density and whatnot, but I'll go into that later. And the sounding data I pulled from the University of Wyoming, their website that's online, and the radar data I pulled from the Amazon Web Services. So kudos to that. And I analyzed it all with GR2 Analyst, which is a very good program. And I'll show you what that interface looked like for me. So whenever I loaded the radar data for a certain time onto my computer, I would put it in GR2 Analyst, and this is the screen. So for the first panel in the upper left that I labeled A, that was just a base reflectivity that you would see. On this one, you can see that there is a hail core in there with the very high white and purple colors. Those are, the white is in the 70s range and the purple is in the 60s. And the B panel, that was the correlation coefficient, or CC as abbreviated. And then in the panel C, that would be the mesh, or the maximum estimated size of hail. The algorithm for this storm, the maximum estimated size of hail was 4.53 inches, which is pretty large, although the report was only 2.5 inches. So we'll get into that. And then the D panel on the lower right, that was, oh, my apology. C was the Ville density, so vertically integrated liquid density. That was in the lower left C, and the D is actually mesh. My apologies. They look very similar in color, so I got it mixed up for a moment, but that's what I was looking at. So I would pour all of the information that I found into an Excel spreadsheet. And so I would just record like the heights at the 50, 60, and 70 dBz levels. And you can see I made these box plots that show the range of the maximum heights for those echoes. And the average for the 50 dBz was about 43,000 feet, and for the 60 was about 35,000. The 70 had a little bit of a wider range, which means it's probably not as good as an indicator as the 50 and 60, since those are more narrow, but there's a clear difference between all of those. as you can see by the range of the box and not just the whiskers, just the boxes. All right. And from the dual polarization perspective, so these would be parameters that were introduced in 2014 when the National Weather Service radar system was updated to dual polarization capabilities. That's where correlation coefficient and ZDR were introduced. Correlation coefficient was typically very low. I mean, in previous studies, they said that I think for hail sizes about 1 inch in diameter and larger, you expect them to be about 0.9 for a correlation coefficient. So naturally, you would think the larger in diameter the hail, the lower the correlation coefficient would be. And that proved true for this. The average is around 0.68 correlation coefficient. So that was quite low. And the range for that was typically between 0.6 and like 0.82 or something like that. So very, very low, which is good. We were hoping for some result like that. And the ZDR, typically previous studies demonstrated the ZDR was around it was non-zero, but it was typically between like value around 1, whether it be positive or negative. In this study, a lot of them were negative and it hovered around negative 0.82. So a lot of values were around between negative 0.5 and negative 1, which is another interesting result. Mesh and Ville density tend to be very popular parameters to look at for very large hail. Ville density in this case, which is the right plot on the side of the screen, had much more range than expected. So that means it's probably not as good as an indicator of large hail, since I think just the box alone, ignoring the whisker, it went from like 7.5 to 13 kilograms per meter cubed, which is quite a large difference. But mesh, on the other hand, thankfully had pretty good. It was about what we would expect. I mean, the average is just short or right at 3 inches, which is good since most of these reports were 2.5 inches and above. And the box ranged from about, I think, like 2.25 to a little below 4, which is excellent because a lot of the reports were in like the 2.5 to 3.25 range, and there were very few that were much larger than that. So, although while I was going through all these reports on GR2 Analyst, I discovered that there were numerous errors in the report times. So I would run into problems as in the report would be like at 1300 UTC, but the radar data indicated that the storm was over that specific location maybe 20 minutes earlier. So of course you can attribute these to human error. Like people aren't gonna automatically report the hail as soon as it happens, but there were some that were very odd, and so those cases had to be deleted. Like one report was an entire 24 hours later than the radar data indicated, so that was quite strange. So I pulled it up on GR2 Analyst and there was nothing there. So I had to do a lot of searching, and it took longer than expected to figure out where all the reports are located and if it was the correct time and if there was the correct radar data to be looking at. So perhaps the National Weather Service should consider quality controlling some of their larger hail cases, because the database that I obtained all these hail cases from is the storm data base that's from the National Centers for Environmental Information. National Weather Service offices put their reports into that database. So perhaps once they get the much larger hail reports, they should maybe consider seeing if it matches up with the radar indicated reflectivity and whatnot. And this project enhanced existing knowledge and research at the National Weather Service Boulder office, because very large hails haven't been studied before over northeast Colorado. There was one, I think, that studied a specific storm in Fort Collins, but never over like the entire northeast of Colorado, where much of the large hail falls. So in summary, the project was the first of its kind in analyzing the very large hail events over northeast Colorado in the dual polarization area, which would be 2014 to the present. So I did look at a couple of cases that were from this summer in 2020. Some of the reports had wrong times and didn't match up with the data. Sometimes the location was slightly off, so the time would be correct. But if you were looking at the data, the storm wouldn't be quite over the location, it'd just be like a mile west or something like that. And the research is consistent with and expands upon previous studies before and after the dual polarization era. So for example, the mean correlation coefficient value, or CC, was below 0.7 for very large hail. And as I said in the past, typically the threshold you look at for that would be 0.9, but again, that was for 1 inch and larger hail, and not 2.5 inches and larger. So the next steps for this project, the National Weather Service in Boulder plans to apply these results in future convective events to improve severe thunderstorm warnings, so more large hail events can happen this summer. Typically, these events happen between May and September of every year, so they could still use them this year, and then hopefully they'll get to expand upon it next year in 2021 with the next Hollings Scholar. I hear they might be looking at 2 inches in larger hail cases, so they'll be adding those on, which will be adding quite a lot of cases on there. Personally, I plan to attend grad school and earn at the least a master's degree in meteorology, and ultimately I want to become a NOAA researcher, so doing this Hollings project was like a little dream. Finally, I'd like to thank my 2 mentors, Paul Slatter and Robert Klayla, for providing all the resources I needed and helping through everything, especially when I got very confused in the beginning with the radar times and scans not matching up with the report times. And especially I'd like to thank the NOAA Ernest F. Hollings Undergraduate Scholarship Program for giving me this opportunity to complete this project and to present it to you all. Thank you.
Our next speaker is going to be Caroline Jones from Virginia Tech, hosted by the National Weather Service in Phoenix. And her talk is Impact-Based Climatology of Vicinity versus Prevailing Thunderstorms at U.S. Airports. So Caroline, can you hear us?
Yeah, can you hear me?
Yes, you sound good, camera looks good, and we see your presentation right now. Looks good. The floor is yours.
Okay, great. So yeah, I'm Caroline, and I did my presentation on the climatology of vicinity versus prevailing thunderstorms at continental U.S. airports. So the motivation behind this project was we wanted to better understand the climatological frequency and duration of vicinity versus prevailing thunderstorms. We wanted to determine if regional differences exist throughout the continental U.S. and what the implications of these differences might have on convective aviation. So basically, we wanted to see if there was a way to improve TAFs. And so this little graphic I have on the right is to help visualize the 4 different storm types that I'm going to talk about throughout this presentation. So first is VCTS only. And this is a storm where if you imagine the airport at the very center of this circle, there's only strikes within the 5 to 10 mile ring around the airport. There's no strikes within 0 to 5. For VCTS first, that means that the first strike of the storm is going to be within that 5 to 10 mile ring, but the rest of the strikes throughout the whole storm can be anywhere from 0 to 10 miles. For TS first, it's basically the same, but of course the first strike is within 0 to 5, and then the rest of the strikes can be anywhere from 0 to 10. And TS only means that the only strikes that are occurring during that storm are within 0 to 5 miles from the airport. So also another reason for looking at the lightning climatology surrounding airports is because thunderstorms are the most significant weather-related aviation impact, and you can see that in the little chart down there. And it'll be helpful to better understand thunderstorm climatologies as we look at the relationship between creating TAFs from digital aviation services. Okay, and so here are the research questions that guided our study. So first is what are the characteristics of thunderstorms that produce lightning only in the vicinity of an airport versus thunderstorms that also produce lightning within 0 to 5 miles of an airport? And so that would be comparing VCTS only to the other 3 classifications that I outlined. Also, what % of storms first strike is within 5 versus 5 to 10 miles? What % of storms only have lightning within 0 to 5 miles? What % of storms only have lightning from 5 to 10 miles? And is there a greater chance of VCTS only storms in the desert Southwest and Intermountain region relative to other regions of the continental US? So the methods of how we got our data, First of all, our time period was 10 years from 2010 to 2019, and we looked at the warm season lightning, which we determined was from April to October. And then we got our lightning data from NLDN, which is the National Lightning Detection Network. We ended up with almost 35,000 storms from 53 continental US airports. And we defined these storm periods with the beginning of the storm being the first lightning strike that is within 10 miles from the airport. And the end of the storm is the last lightning strike that is within 10 miles from the airport. And so in order to have a distinction between storm types, or one storm from another, we mandated that at least 1 hour had to pass between the last lightning strike of the old storm and the first lightning strike of the new storm. So in doing so, we ended up with about 6,100 one-strike storms that we ended up eliminating for this analysis. And that ended up being a total of about 18% of the original almost 35,000 storms. And then as for our airport site selection, we first looked at the list of the top 50 airports for total operations and the top 50 list for commercial passengers. And we combined those two lists into one. And there was a fair amount of overlap. So we ended up with roughly 65 or so sites. And then we added 4 more Southwest and Intermountain into the top, that were in the top 100 of commercial passengers, just so we had more sites in the Southwest, since that was a main area of focus for us. And those were Albuquerque, Tucson, El Paso, and Palm Springs. We also said that each site must be a TAF site in the continental US, and all must be at least 10 miles from each other. And lastly, they must have at least 50 storms with greater than 1 strike. So this is how we ended up with ultimately only having 53 storms that we looked at. Okay, and so here is looking at some of the data for a specific site, and this is for Phoenix's site. And so the total storms for Phoenix from this time period, from 2010 to 2019, they had 195 storms. And the breakdown of the percentage of each type of storm is best illustrated in that little pie chart. And so I want you to make note of the red slice in particular, which is the VCTS only slice. And it's 36% here, which is actually one of the lower ranked VCTS only storms in the Southwest Intermountain region, but it'll give you a good frame of reference when we move on to the other results. And as you can see in the box and whisker plot, the VCTS first storms typically lasted the longest, and then followed by the TS first, VCTS only, and then TS only. So this is one of our main points that we discovered from this research, and it's that VCTS only storms are most likely in the Southwest and Intermountain regions. So, and this is with the preface that 85% of all storms first strike is within 5 to 10 miles, and that's regardless of region, it doesn't matter. But despite this, despite the majority of storms around airports experiencing their first strike within 5 to 10 miles, the Southwest and Intermountain region had a significantly higher average of VCTS only when compared to the inland and coastal regions. And so you can see right there in the box that 37% of the time they had VCTS only storms, compared to 30%, almost 26%, and 30% even for the whole continental US. And then to the right there, I have a screenshot of our data from Excel, and it's color coded to each region. This is just the top half. We're going to get more into it on the next slide. But just for reference, the yellow corresponds to the Southwest Intermountain region, the blue corresponds to the coastal region, and the green corresponds to the inland region. So here we have all 53 sites, and it better illustrates just how dominating the Southwest and Intermountain sites are in the top ranks, and how inland sites are for the most part in the bottom ranks. And so as you can see, the Southwest Intermountain region makes up 11 of the top 13 ranked sites with Deer Valley being an outlier down at 25. The top ranked site is Palm Springs with almost 52% of their storms being VCTS only. So that means over half the time their storms are VCTS only. But this was a bit of an outlier because the number 2 rank in Las Vegas was 42%. And that was more typical as you go down and not much of a jump from there. And from these findings, there's a couple of notes that we can make about maybe possible implications this could mean for the Southwest and Intermountain areas. And so a positive implication could mean that the VCTS TAF groups might verify more often because we have more VCTS only storms in that region. But using lightning within 5 to 10 to predict lightning within 5 might result in more false alarms. Again, because there's a greater chance of the storm being VCTS only and staying in that 5 to 10 ring around the actual site. Okay, so here we're going to talk about the lightning counts. And so the lightning count is by storm type. And then the Southwest and Intermountain regions are dashed, and the inland and coastal is combined into one, and it's solid. And we combined the inland and coastal because they were very similar. As you can actually see, they were about as similar as the VCTS only and TS only. So the red and blue lines are even between Southwest Intermountain and inland and coastal combined. But overall, you can see that, like the headline says, that Southwest and Intermountain storms tend to produce less lightning, even though VCTS only and TS only are pretty similar. The VCTS first and TS first distinctions show that Southwest Intermountain do, in fact, produce less lightning on average. Okay, and now we're going to talk about the storm durations that we found. And so the VCTS only storms are about 2 to 3 times shorter than those that produce lightning within 5. So again, that's the other 3 types of classifications. And then the Southwest Intermountain cases shown in this graph have slightly shorter durations than other regions. And you can see this again with the data that's listed below. So in conclusion, I'm going to answer some of those research questions that I had at the beginning. So the first one, again, was what are the characteristics of thunderstorms that produce lightning only in the vicinity of an airport versus thunderstorms that also produce lightning within 0 to 5 miles of an airport? So we found that VCTS only storms generally produce about 10 times fewer strikes within 10 miles and last 2 to 3 times shorter than storms that produce lightning within 5. And then what percent of storms first strike is within 5 versus 5 to 10? And we found this to be on average about 15% of the time. And there was a range of 11 to 19% when you look at all of the different sites that we analyzed. And then what percent of storms only have lightning within 0 to 5 miles? This was very minimal. You might have seen in the pie chart from Phoenix that they only had this happen 2% of the time. But throughout all the sites, it was less than 3% of the time. And what percent of storms only have lightning within 5 to 10 miles? So this varies. This is what we were talking about with the VCTS only. And it varies anywhere from 20 to 42% roughly. However, we did have that outlier that was the highest ranked one at Palm Springs. And lastly, is there a greater chance of VCTS only storms in the desert Southwest and Intermountain region relative to other regions of the continental US? And this is a resounding yes. There definitely is a greater chance of VCTS only storms, as can be seen when you look at the different averages and when you look at the rank order. So the next steps of this project would be to add more sites to fill in gaps and better represent the entire continental US. There was a couple of states that we ended up leaving out just because we didn't have a site for that area yet. And eventually we want this to be a more impact-based climatology. So we would look at the duration and intensity of wind gusts and reductions in visibility due to dust. So this is definitely important in the Southwest, something that I have never seen living in Virginia. but something that'd be really interesting for me to see. So you can see a picture right there of a dust storm moving in, and that graphic shows dust storms in the Phoenix area. And we'd also want to look at the range at which storms may cause impacts. So even if there is lightning that's greater than 10 miles away from an airport from a storm, would the airport receive any impacts from that storm? And then lastly, we would look more into the seasonal and diurnal variations to assist in FAA staffing schedules. All right, I also want to thank the NOAA Hollings Scholarship Program for this opportunity, and special thanks to my mentors, Paul, who helped me with so many questions about Python, probably at least 1,000, and then Larry for helping me put together this presentation and helping me with the finishing touches. And if there's any questions, I'll be happy to take them.
All right, we're going to go ahead though to our next talk, which is Callan Parker from Penn State University, hosted by the Storm Prediction Center. And this talk is creating and exploring the climatology of SPC watch products. So we see you, Callan.
See my screen.
Yeah, you should get a pop-up box. There it is.
There we go. Okay.
See your screen. You are good to go. Floor is yours.
So as mentioned, today we'll be looking at creating and exploring a climatology of SPC watch products. So our objective with this is to look at how severe thunderstorm and tornado watches have evolved from 1970 to 2019 by season and region in terms of number of watches, watch size, duration, and verification statistics. Our goal with this is to provide insight on the evolution of severe weather and our ability to forecast severe weather threats over time in hopes of building a more weather-ready nation. Convective watches are issued by the SPC when conditions are deemed favorable for multiple events of organized severe convection. So for a tornado watch, this would be if 2 tornadoes or if 1 EF2 tornado or stronger is expected. And for a severe thunderstorm watch, this is if at least 6 events of severe hail or severe wind are expected. And this should be for a size of at least 8,000 miles squared for a duration of at least 2 hours. In the early 2000s, watches transitioned from having a parallelogram extent to a county-based extent with an accompanying parallelogram. So for this study, we are only concerned with the parallelogram extent of the initially issued watch. So that also means that there are no watch extensions. Our watch dataset used was provided by Andy Dean and includes all available data from 1/1/1970 to 6/1/2019. So with that, all of our yearly plots will be excluding 2019 because it's incomplete. For verification, we use the reports data set from the SPC WCM page, which is currently maintained by Dr. Patrick Marsh. To split watches by region, we chose 6 regions, being the West, the Northern Plains, the Great Plains, the Midwest, the South, and the Northeast. And these were chosen for having similar environments and storm climatologies based on previous literature. For the watches that fall on the border of 2 or more regions, they're simply just sorted into the region in which it has the most overlapping area. To split watches by season, this was based on the meteorological definition of seasons, and the watches were sorted by their start date. For the verification statistics, we've so far only explored this for tornado watches, but it includes percent verified, or PV, which is equal to the watches containing a report divided by the total number of watches, and then probability of detection, or POD, which is equal to the tornadoes found in watches divided by total tornado reports, and both of these are on a yearly scale. All maps that you'll see were created in ArcGIS Pro by converting our dataset to a shapefile. We also utilized ARC features such as count, overlapping features, polygon to raster, and raster calculator. So we'll start by those maps. Here we have severe thunderstorm watch count by decade. And if I jump from the 70s to the 80s, you'll notice a general increase across most areas in the country, which this trend then continues into the 90s. As we move into the 2000s, most areas stay somewhat steady or start to decrease, other than the Northern Plains, which still continue to rise. And then into the 10s, everywhere again generally sees a decrease. But no matter what decade you look at here, the Great Plains remains the severe thunderstorm watch maximum. For tornado watches, the first thing you'll notice is that there are two areas of count maximum, one in the south and one in the Great Plains in the 70s. As we advance forward, this area starts to merge into one and then is officially one large region by the 90s. You'll also see the count generally went up into this decade for most areas. And then as we advance to the next decade, count starts to go back down and the watch maximum transition to be mostly over the south region. The same trend continues into the 10s. We can also look at this graphically. Here you can see that same surge in severe thunderstorm count across most regions throughout the 70s and 80s. Something you couldn't see really from the maps is this secondary peak in tornado watch count in the 2000s, which we think may be linked to having a better understanding of high shear low cape environments, especially because this peak is most noticeable across the south. Something else that you may see here is that tornado watches actually outnumbered severe thunderstorm watches in the Great Plains in the early 70s, and then again for the south in the last 2 decades, which is unique to these regions. These plots are also nicely supplemented by maps of change. So if we highlight from change the 70s to the 80s, you'll see a slight decrease in this time across CONUS, and that's highlighted by most areas in the country showing up in this green color. From the 80s to the 90s, that's when the surge really took place. And again, this is most noticeable across the South and the Great Plains as identified by these darker green colors. When we look at from the 90s to the 2000s, according to the plot, this time period looks somewhat stagnant across CONUS, but most areas actually saw some form of increase or decrease in this time, with the decrease being most prominent across the South and the increase being most prominent across the Northern Plains. For tornado watches, from the 70s to the 80s, we saw a gradual decrease across CONUS at this time. Again, this is mostly a result of the South and the Great Plains seeing a decrease as indicated by these purple colors on the map. From the 80s to the 90s is when we saw a surge in tornado watches. Again, this is also mostly in the South and the Great Plains as indicated by these deep green colors. Then from the 90s to the 2000s, the general trend across CONUS was a decrease, but this is really only a product of a major decrease across the Great Plains as indicated by the deep purples. Areas such as the South were actually a bit more steady or even saw an increase as indicated by the greens, and these areas in green are also regions that are more prone to high shear low cape environments. We can also take a look at count by season. Here you'll notice that severe thunderstorm watch trends for the spring are fairly consistent across regions other than the Northern Plains, which started to see a surge in the late 90s and into the 2000s. Here on the springtime tornado watches graph, you'll notice that the South has actually started to outnumber the Great Plains in springtime tornado watches in the last few decades, which may just be to a few inactive seasons across the Great Plains. Moving on to summer, again, trends are fairly consistent across regions for severe thunderstorm watches until we get to the 90s through the early 2000s. Here, there starts to be some divergence in trends across regions, with the Northeast, the South, and the Great Plains seeing a decrease and other regions either staying steady or seeing an increase. For summertime tornado watches, there is a large rise and fall centered on the 90s, which is largely a result of the Great Plains. Again, you can see the secondary maximum into the 2000s, which can be seen across many regions, including the Great Plains, the Midwest, and the Northeast. For the fall, again, we see the surge that is present across all seasons, followed by a fall in the last few decades of severe thunderstorm watch count. What's interesting about the drop-off is that it's not noticeable across all regions, mostly being the Midwest and the West, which have actually remained mostly steady in their counts for the last few decades. For fall time tornado watches, the overall trend is really mostly determined by the South, which isn't too surprising, climatologically speaking. But again, also a notable rise and fall centered on the 90s across the Great Plains. For severe thunderstorm watches in the winter, you'll notice that there is a much sharper rise and fall off for this season than the other seasons, with this mostly being a result of changes across the South and the Great Plains. What's interesting though is that despite the falling trend in recent years, regions such as the Midwest and the Northeast have been a bit more steady or actually rising. For wintertime tornado watches, again, trends are pretty much mostly determined by the South. But what's interesting here is that regions such as the Midwest have been on the rise generally in watch count for the last few decades. So now we'll take a look at watch size. The first thing to notice here is that tornado watches are pretty consistently larger than severe thunderstorm watches, with both types seeing their peak in the late 70s to early 80s. This decrease throughout the 80s, we think, is due to improved forecasting from advancements in satellites. We then see another drop-off in size again in recent years, which may be linked to the new county-based warning method. When looking at watch size by region, I don't have them shown, but the trends across the South, the Northern Plains, the Great Plains, and the Midwest all closely mimic CONUS. So on the right side, I have the Northeast and the West, and here you'll see that the Northeast has seen a secondary maximum in severe thunderstorm watch size in the late 90s and early 2000s, which is really interesting because this pattern doesn't show up for tornado watches. Also across the West, both watch types have been seeing a general increase in watch size throughout the time frame. What's also unique to both of these regions is that it's not unusual for severe thunderstorm watches to be larger than tornado watches. You can also look at watch size by year, and the most notable thing from both of these plots is that watch size has generally gotten more variable with time, which we think may be due to improved forecasting and forecasters better being able to fit a watch size to a specific event. With that, both watch types have had their largest and smallest watches in the last 15 years, and even though it's not here, this trend is very consistent across regions. We can also take a look at duration by season and by region, and you'll notice here that median duration for both watch types for all seasons and regions falls between 5 and 6 hours. Something else you'll notice is that tornado watches are much more likely to have long duration outliers than severe thunderstorm watches. This is most notable across the South and the Great Plains, and then across all seasons except for the winter. When looking at watch duration by year, again, you can see all these long duration outliers. You'll also notice that the trends in both of these plots are very similar, mostly being this reduction in variability across the 70, especially on the low end of duration, reduction in variability in the early 80s, a reduction in variability in the late 90s to early 2000s, and then a jump in median watch size and in the longer duration, or jump in median duration and in the long duration watches in 2005. And again, I don't have them here, but these trends are very consistent across regions, which lead us to believe that it's most likely a result of policy changes. Lastly, we'll take a look at verification. Here you can see that PV for tornado watches has generally been increasing throughout time, which again, that's the number of watches containing a report divided by the total number of watches in a year. So this increase means that our forecasting skill is likely increasing, which is what we want. POD has generally been increasing until about 2011, where we started to see a decrease. And again, this is the reports in a year that fall in a watch divided by the total number of reports. And we believe that the recent decrease is likely linked to years being a little bit less active, having less tornado outbreaks and less violent tornadoes. So in summary, watch count saw a surge for both watch types throughout the 80s and early 90s. Since then, trends have been a bit more variable seasonally and regionally. Trends in watch size are consistent across most regions other than the Northeast and West, and tornado watches tend to be larger than severe thunderstorm watches overall. Watch duration has been much more variable with time than it is across different seasons and regions, and recent reductions in POD for tornado watches may be linked to less high-end events. My next steps are to continue work with the verification statistics specifically for seasons and regions, and also for severe thunderstorm watches. We also want to explore other watch parameters such as watch start time by season and region, and also watch probabilities, which began in 2003. I also want to present these findings at the AMS conference. I'd like to thank both my mentors for allowing me to participate in this project and just being awesome, and also again to Andy Dean and Patrick Marsh for providing the data used for this study.
Emily McCutcheon from the University of Oklahoma, hosted by the National Weather Service in Fairbanks, Alaska, an exploration of the hot, dry, windy index and its applicability to the Alaska wildfire environment. Hi, Emily. We see you and we see your presentation. Cannot hear you. You are muted. You'll have to unmute. Oh, we'll have to unmute you. There you go. Try now. There you
Excellent.
go. We had you muted. That's our fault. So the floor is yours.
All right, thank you. My name is Emily McCutcheon. I'm a meteorology student at the University of Oklahoma. This summer, I've had the privilege of working with the forecast office in Fairbanks, Alaska, examining this new hot, dry, windy index and how it can be used in Alaska wildfire forecasting. Today, my focus is going to be on how does hot, dry, windy, or HDW for short, and its percentiles compare to wildfire growth. Alaska is known for ice and snow, but it also deals with a lot of significant wildfire each and every summer. If you look at this figure on the right, it shows the total amount of area burned in acres each summer, with the red bars indicating summers that had over 1 million acres burned. And as you can see, as you progress through the time series, the frequency of these million-acre fire seasons is increasing, likely as a result of climate change. Thus, this is important to understand going forward as we deal with more. Alaska also deals with quite a lot of quirks compared to fire forecasting in the lower 48. One of the large ones being their management strategy. If you look at the map on the left, all of the areas with some sort of color contour are the only areas that get suppressed. And as you can see, a lot of landmass, there is virtually no fire suppression. And this is for the reason that nobody's living there for there to be life or property to be affected by these fires. Thus, fires are generally left to burn so that way the ecological benefits can be reaped. There are many different ways to indicate potentially dangerous fire activity that use different sets of data. In the lower 48, the Haines Index and National Fire Danger Rating System are quite popular. However, in Alaska, we tend to prefer the Canadian Forest Fire Weather Index because of the fuels and how different the fuels are. In the lower 48, a lot of the fuels tend to be dried and cured, whereas in your more Canadian and Alaskan fires, the fuels are generally still pretty green and have a lot of moisture in them, which leads to different fire behavior. So a brief overview of the Canadian Fire Weather Index. It consists of 3 basic codes: your fine fuel moisture code, your Duff moisture code, and then your drought code. Each of these correspond to different fuel sizes. So your fine fuel moisture code changes on shorter time scales, those being hours to days. But they also look more at your smaller fuels, such as your grasses, where you get into your drought code, which is affected on the order of days to weeks. And that would be more significant for your boreal forest, where there's a lot of trees. What I used out of this in my study is the buildup index, or BUI, which is a combination of Duff moisture code and drought code. And this BUI is a very good indicator of how primed the landscape is for fires and how susceptible to fires the landscape is. So what exactly is hot, dry, windy? It's a combination of 2 meteorological variables, so vapor pressure deficit, or VPD, and your wind speed. Your vapor pressure deficit is your saturation vapor pressure minus your observed vapor pressure reported in hectopascals. And it accounts for both moisture and heat because it has a dependence both on relative humidity and temperature. As you can see in the figure on the right, you can have the same level of relative humidity. However, at different temperatures, your vapor pressure deficit actually increases because your saturation and vapor pressure scales exponentially with temperature. This vapor pressure deficit has been used a lot by botanists in measures of moisture stress on plants and used to create optimal growing conditions in greenhouses, and thus would be an excellent indicator of how much drying is occurring within your fuels at a given period of time. Your windy conditions are simply covered by wind speed. And then at its most basic, your hot, dry, windy is the multiplication of your vapor pressure deficit and your wind speed. Getting in a little bit into the nuts and bolts of the calculation, I constructed hot, dry, windy for the state of Alaska from hourly ERA 5 reanalysis data over the period of 1980 through 2019 for each fire season, which I defined as from May 1st through September 30th. And for each hour at a given grid point, I looked at the lowest 500 meters of the atmosphere, or 50 millibars, and found the highest vapor pressure deficit and the highest wind speed value below an inversion. Above an inversion is not going to really affect the fire and is thus ignored. And then from these two highest values, they're multiplied together, and that makes your hourly hot, dry, windy value. And then your daily hot, dry, windy value is selected from this hourly value. And it's the highest hourly value. And a day is considered from 4 a.m. to 4 a.m. local time, or 12Z to 12Z. And then on top of this, I also calculated percentiles for each day because they're often used in the contiguous United States and supposedly correlate better to fire growth. I chose to evaluate how hot, dry, windy relates to fire growth through a series of 10 case studies throughout Alaska. I used 4 primary data sources: the final reported fire perimeter from the Alaska Interagency Coordination Center, MODIS thermal anomaly detections, or simply MODIS detects, surface observations, and ERA5 reanalysis data. MODIS detections within a final fire perimeter were used as a proxy for fire growth, so I would count them for each day. And then the surface observations were in daily summaries. And so I found the center of the fire geometrically, and then located the nearest set of surface observations and kept on jumping from station until I found the closest station with complete record, and then pulled both the buildup index and the precipitation amounts from that surface observation station. And then finally, I pulled the hot, dry, windy value and the percentile for each individual day from the grid cell closest to the center of the fire. So the first case study I looked at was the North Dag fire, which burned during the summer of 2004 in the central interior, which is boreal forest. And as you can see, it began as a lightning start fire. Can everybody see my cursor?
Yes.
Okay. So it started around June 15th. However, looking down at this precipitation graph, there was some sort of precipitation event that squelched the fire early on. And then there was a period of more favorable conditions, as indicated by the higher hot, dry, windy, but the fire was likely too small to be able to take advantage of it until this point in late June, where we see our first spike in MODIS detections, and it's well correlated to a spike in hot, dry, windy, both its percentile value in the second plot here and the raw hot, dry, windy value in the plot above it. This dotted blue line represents the MODIS detections. And then the top plot represents hot, dry, windy, the second plot the percentile values, the third plot the buildup index, and then the fourth and final plot is precipitation. So you can see there was this first period of growth, and then there was a precipitation event that again squelched the fire, cooled it down a little bit, but conditions continued to be favorable, and you see another surge in MODIS detections, and that is associated with a general increase in hot, dry, windy. However, it looks rather modest in the raw values, but it can really shine here within the percentile values. And this is a case of where you can get similar information out of both hot, dry, windy and its percentile, but percentiles are going to communicate that risk much better than hot, dry, windy in and of itself. These two periods of growth are then followed by a really significant precipitation event at the end of July, which really squelched the fire. And you can also see that the landscape became less susceptible to fire in this fallen buildup index. And there's not a lot of growth in this period. Days where there's not MODIS detections are days where there was really not any fire activity to be considered. And then you finally see these two flare-ups at the end of August, at the beginning and end of August, which are separated by yet another precipitation event. And both of these are correlated with pretty high hot, dry, windy values. So overall, what we do see is that whenever there are increases in hot, dry, windy value, whenever there are increases in MODIS detections, there are associated increases in hot, dry, windy value. However, just because there's an increase in hot, dry, windy does not mean that there's going to be an increase in MODIS detections. You can see how it spikes all over the place, regardless of if the fire is growing or not. And this really highlights the importance of context when looking at this information. I also pulled another chart of a case study, and it looks rather similar to the last one. The spikes do not align as well, and this is fairly representative of what I saw with the rest of the case studies and really continues to illustrate this point of where increases in MODIS detections generally have some association with an increase in hot, dry, windy, but it's not very cut and dry. Finally, I attempted to do a bulk analysis of all of this. And this is a scatter plot of your MODIS detections within a particular sub area called a predictive service area. I selected one from the northeast interior here where there were a lot of fires. And I looked at the mean hot, dry, windy yearly percentile value for that area, as well as the MODIS detections. And you can see a general positive trend, but it's not very strong. Furthermore, the different years are indicated by different colored series. You can see in the red series and the purple series, there's a positive trend, but in the yellow series, there's a negative trend. And that would be something that would be interesting to look at in the future, to look at why certain years correlated with hot, dry, windy a different way. But as you can see, it really highlights the importance of that context, where just because there was a high hot, dry, windy doesn't mean you're going to get high detections out of it. So in conclusion, your fire growth periods generally occur during periods of higher hot, dry, windy. Your periods of high hot, dry, windy don't necessarily mean a period of large growth. Your MODIS detections align better with increases in the hot, dry, windy percentile, as opposed to increases in raw hot, dry, windy. And your other environmental factors are key to determining if there's going to be if your spike in hot, dry, windy is going to translate to fire growth. So hot, dry, windy may be best used as a means to rule out a big growth day, as opposed to finding a big growth day. Finally, I would like to acknowledge all of my mentors for their support, as well as Jay Charney, who helped me assure the correct calculation of hot, dry, windy, and Chris Moore, who helped me select case studies. And I would like to thank the Ernest F. Hollings Scholarship Program, as well as all of my mentors and everybody involved for having the flexibility and creativity to switch this internship to a virtual setting due to COVID-19. With that, I have concluded. Thank you for your attention. And if you have any further questions that I'm unable to answer today, here are my emails. Thank you.
So we have Miles Langfeld from Texas A&M University, hosted by the National Weather Service in Springfield, Missouri, and he is doing Flood Diagnostic Innovation Project. So Miles, we can see you.
Can you see my screen?
Yes, looks good, and we can hear you as well.
Okay,
so
perfect.
The floor is yours.
All right, well, hello everyone. My name is Miles Langfeld. I am about to be a senior meteorology major down here at Texas A&M University. I have been working on this flood diagnostic innovation project alongside all the staff at the forecast office in Springfield, Missouri this summer. So a little bit of background on this project. The topography and the geological characteristics of the forecast office in Springfield, Missouri, their county warning area, really make this area a flash flood hotspot. Looking at this elevation map, most of the county warning area is located in the Missouri Ozarks, and also there's very little topsoil, so runoff is very heavy in this area, again, making this a flash flood hotspot. Flash flooding is also the most frequent weather-related cause of death in the Missouri Ozarks, and any heavy rainfall over hundreds of these small and rugged watersheds can lead to pretty rapid rises in local creeks and streams in the county warning area. There's also thousands of low-lying bridges and crossings that can become susceptible to flooding when this heavy rain does occur, which can become a danger to motorists on these county roads and state highways. So it is with these impacts in mind that an initiative was taken to gather detailed information on sensitive floodpoints within this area to help forecasters issue more accurate and precise warnings throughout the county warning area. So the objectives of this project were to create a collection of flood-related heat maps. These heat maps would include reports and fatalities for some selected individual years and some time periods using storm data from the National Weather Service Storm Data Program. And these maps were created inside of ArcGIS Pro. We also developed customized basin shapefiles specific to flood-sensitive locations that can be utilized in AWIPS and overlaid with rainfall amount and rainfall rate footprints. AWIPS, these customized shapefiles can give warning forecasters an understanding of the excessive rainfall that is being funneled into these specific floodpoints that are hazardous to the public. This info can then be relayed to any core partners, the public, via traditional National Weather Service products, social media, and other means of National Weather Service communication. With data collected from StreamStats and Google Earth Pro, we would then calculate a flash flood sensitivity index for each floodpoint and then perform rank analysis on each floodpoint categorized by that flash flood sensitivity index. This can give the warning forecasters in the Springfield, Missouri County warning area an initial awareness of how flood prone a location typically is. And then after all that was said and done, we would then build a flood diagnostic catalog containing images and information on each of those floodpoints and the known impacts of those floodpoints. So looking at some CONUS maps, the one on the left is a kernel density map of the 2007 to 2019 flash flood reports. When looking at that map, we can see a few hotspots that come up in the country. So you can see a hotspot again over southwestern Missouri, which is where the CWA is located, and then also in the northeastern states, and then in south central Texas up into the DFW area. On the right side is a CONUS kernel density map of the 2007 to 2020 flood fatalities. So the most notable is the areas in Texas. There are some pretty notable events that are producing a maxima in that area, but there's also a maxima in western Arkansas, eastern Oklahoma, southern Missouri that extends up into the CWA that is notable as well. And so again, with these impacts in mind, we can move down to a state and CWA scale. So looking at the Missouri kernel density map of the 2007 to 2019 flash flood reports, we can see that the areas highlighted in the CWA, which is the southern southwestern portion of the state, do include the most flash flood reports in the state of Missouri. There's a maxima located in Kansas City, but overall the southwestern and southern portion of the state includes the most flash flood reports. On the right is a kernel density map of the 1996 to 2020 flash flood fatalities with the individual points located on the map as well, categorized by the number of fatalities associated with each point. So there really are fatalities located across the whole state, which again makes it imperative that our warning forecasters understand flash flooding in the area, which areas are more susceptible and which flood points are the most sensitive to flash flooding in the area. So these are the flood points. We analyzed and cataloged about exactly 308 flood points across 34 Missouri counties. These included any low water crossings, county roads, state highways, and Missouri Department of Transportation routes. There are many more flood points within the CWA. You could say hundreds, thousands more flood points inside the CWA. But really the goal was to analyze a widespread spatial resolution that allows our warning forecasters at the WFO Springfield enough information that covers most of the CWA during excessive rainfall events. So next I'll talk about the different types of crossings that we analyzed. So the top left are our two ventilated weirs. These actually during flash flooding events can become clogged, and so they're actually become more sensitive. Our bridges are usually our least sensitive of the group because they're usually higher off the ground and more water can flow underneath. Then we have our box culverts and then our unvented fords, which are usually our most sensitive because they are built right on top of the bank and water flows over them pretty easily. So to start the process of this project, we used StreamStats, which is a web-based geographic information systems application produced by the United States Geological Survey. So inside of this application, we can indicate a lat-long point of a specific flood point that we want to analyze. It will then develop a customized basin shape file for that flood point, which is that picture on the left. Then the picture on the bottom right, we then collected basin characteristics and peak flow statistics for each of those flood points, and then inputted that data into a Google spreadsheet with some prepared equations to calculate that flash flood sensitivity index. So the flash flood sensitivity index itself, it takes into account the 25-year discharge. We chose the 25-year discharge just as a random starting point for a flow that we thought would be a danger to motorists crossing the road. The basin size is also taken into account, which is in square miles, and then the height of the road itself, which is in feet. The height of the road had to be estimated inside of Google Earth Pro because I was not there this summer to go out and measure. But this is our index progression. And then if the flood point type is a tube ventilated weir, just because it is more sensitive to flash flooding, a value of 10 was added to that index. And the image on the right is all of our 308 analyzed points categorized by the flash flood sensitivity index, and then also overlaid on top of the heat map of the flash flood sensitivity index. So then when that was all said and done, we went ahead and built our Flood Diagnostic Innovation Project catalog. So inside of this catalog, we will put images, information on each flood point, such as the name. This is the North Fork River at Highway EE. And then we performed that rank analysis. So this one is rank 6 out of all of the points that we have analyzed. We also indicated if it was a fatality location inside of the catalog, the lat-long position, which type of crossing it is, of course, the sensitivity index, and then some images upstream of the flood point and of the flood point itself, and also an image from Google Earth Pro of the basin shape files and the longest flow path inputted inside of Google Earth Pro. And then we also included some basin characteristics such as the size, the 25-year discharge, and the road height. So some applications of this project is we can overlay the basin and longest flow path shape files with rainfall amounts and rates inside of AWIPS. So this is actually an example of precipitation from a February 12, 2019 event across the southeastern portion of the Springfield, Missouri CWA. So what is shown is those basin shape files, those longest flow path shape files, overlaid on top of the radar estimated storm total. Generally, we saw 1/2 inch to 3/4 of an inch of rain. And these customized basin shape files and longest flow paths are associated with the actual Missouri Department of Transportation crossings that flooded. So what you can do is you can look at the basin shape files, the longest flow path shape files, overlay with those rainfall amounts and rates and AWIPS, and then you can determine and insert the name and location of those at-risk low water crossings into the actual flash flood warning and into the National Weather Service chat, and then also relay them to the public via social media or any other National Weather Service communication products. So here's an actual example of some applications. This is a social media graphic that was actually put out this past June of a flash flood warning in the CWA. So this is of the Bull Creek Basin. So what is shown on the graphic is the basin shape file outlined in white. The red line is the longest flow path within that basin shape file, and then the green polygon is the flash flood warning itself. So it was imperative that we got this out, and this project really helped understand how sensitive this area is to flooding, which areas would actually flood, and then we can see in the impacts, we could designate which crossings would flood and become impassable, and which areas will experience those really rapid rises. So the next steps of this project are to identify and catalog more flood points across the CWA, and also perform some verification on these flood points. And also we want to use the Hydrologic Engineering Center's river analysis system and hydrologic modeling system models to determine an estimate of how much precipitation it would actually take to overtop these low water crossings. Some personal goals: I would like to pursue a career in the National Weather Service upon my graduation from Texas A&M University this coming spring. And some acknowledgements: I would like to give a really big thank you to all the staff at the Forecast Office in Springfield, Missouri. Kelsey for all of your help, Doug for all of your help, and Doug and Corey for all of their previous work on this project. I would also like to say a big thank you to the NOAA Ernest F. Hollings Undergraduate Scholarship Program for granting me this opportunity and providing the funding for this experience. So thank you so much. And with that, I am done.
The next presentation is Gregory Mello. He is from the University of Louisiana at Monroe, hosted by the National Hurricane Center, and his project is searching for undetected preseason tropical cyclones. All right, Greg, I see your screen, you're self-muted.
Can you hear me?
I can hear you. Do you have a camera?
Yeah, 1 second.
Can't see you at this point. There you are.
There you go. Sorry about that.
Excellent. No worries. So we can see your screen. Look good, sound good. So go ahead. The floor is yours.
All right, thank you. So hey everyone, my name is Gregory Mello. I'm from the University of Louisiana Monroe, and I'm a senior meteorology major. And I worked with Dr. Christopher Lancey, who is the chief of the Tropical Analysis and Forecasting Branch at the National Hurricane Center. And we searched for undetected preseason tropical cyclones in the East Pacific. So here's a quick outline of what I'll be talking about today for my project. And here's the objectives. So we looked for undetected tropical cyclones from 2019 to 2000 in the East Pacific. And this was important because we need to keep the National Hurricane Center's database up to date. And this is what really brought on my interest for this project, because I understand the importance of having an accurate hurricane database. And this is why meteorologists at the National Hurricane Center do reanalysis work all the time. And I do believe that there are missing preseason storms from the last 2 decades in the East Pacific, although we did not find too many of those. So I'll give you a bit of background on our motivation for this project. So this year, there was a lot of media attention for Tropical Depression 1E, which made history for being the earliest tropical cyclone to develop in the East Pacific. And we really questioned, was this really the earliest tropical cyclone to develop, or has it just not been discovered yet? And I worked with Dr. Christopher Lancey. He helped me out through the entire summer. And then Dan Mundell also helped us. He gave us the Dvorak classifications for all of the services that we analyzed. And the assumption that we had was that we would find a few missing storms in the East Pacific and possibly one before the record of April 25th. And we used a variety of data sets to identify any potential tropical cyclones. So the methodology, here's the tools that I used for my project. I used TAFB's surface analysis data. I used it to locate the closed lows and their intensity, which was given in pressure in the East Pacific. And I looked at surface analysis data every 6 hours for each day. So to give you an approximation, I looked at about 3,600 surface analysis maps. So yes, it was quite a bit. And I used Gibbs IR visible satellite imagery. And I used this to help determine if the disturbances were organized, such as if there was any banding associated with these disturbances, because tropical cyclones tend to have rain bands that spiral counterclockwise around the low-level circulation. So I used visible satellite for that. And then we used infrared to help us with Dvorak classifications. And I looked at IR and visible satellite imagery every 3 hours to see if there was any missed potential tropical cyclones that weren't shown on the surface analysis data. Then I also used high seas forecast text products from the National Hurricane Center archive. And this contributed wind and wave forecasts for disturbances in the East Pacific. And then scatterometer data from NOAA NWS star was used to analyze for low-level circulations, and it showed the low-level wind speed and direction of the disturbances, so we could really tell if there was a well-defined circulation or if the storm just wasn't very developed. And my results, so we did find 3 disturbances, and only one of those ended up being a potential tropical cyclone. So the disturbance that I will be discussing today is the one that was potentially a tropical cyclone, and it formed along the monsoon trough on May 3rd, 2014. It eventually detached itself after a few days and became a closed low on May 7th. And this system was likely a short-lived tropical cyclone, and it developed on May 7th and dissipated within 18 to 24 hours. The peak intensity was likely from 12 to 18 Z on May 8th, and Dan Mundell, who gave us the Dvorak classifications, gave this a max Dvorak T number of 2.5 on 18 Z on May 8th. So if you guys aren't familiar with the Dvorak technique, it's basically a way to estimate tropical cyclone intensity using satellite imagery. And Dan Mundell is an expert in that, so he helped us out with our project. And I'm sorry I couldn't get this zoomed in very well, but the disturbance I'll be talking about is right here, and it has a pressure of 1,004 millibars. It's about 105 west and 15 north. And I do think this monsoon trough is not attached to the system at this point. It's a closed low, so I think that was an error. And then this was at 18Z when Dan Mundell gave the max intensity for the Dvorak technique. And it shows that there's an elongated trough at this point, and this storm was being sheared off. So it was likely disorganized at this point and was starting to dissipate. So looking at the IR satellite imagery, you can see that there's a huge burst of convection here. So this is IR satellite imagery, shows you the temperature of cloud tops. So the brighter colors that you see here are colder cloud tops. That's likely where you see heavier rain. And at this point, the system was beginning to dissipate. The center was actually to the southwest of this large burst of convection, and it was being sheared off by strong southwesterly shear. And this is the visible satellite imagery for that same time. And it's very hard. I used the visible satellite imagery this summer to look for low-level centers. Anytime the convection began to dissipate, I looked for exposed low-level centers, and it was really hard to find it for this system. But I think the shear just completely destroyed the low-level circulation by the time all of the convection was dissipated. And this is the scatterometer data. So this scatterometer is basically a radar in space, and it shows you surface wind speeds and direction that are about 10 meters above the surface. And there's not a lot of black wind barbs, but if you do see them, there's a few to the south of the circulation, and those are rain contaminated or possibly rain contaminated. And then to the northeast, you can see that there's very strong winds here. The scatterometer is saying that there's about 40 to 45 knot winds here in the northeast quadrant, and this is likely contamination as well, or an overestimate by the scatterometer data, because when you get heavy rain, it causes an overestimation of wind speeds with these scatterometers. So I think that's likely what's happening here. And then the high seas forecast, this provided the wind and wave forecast for the disturbances in the East Pacific, and this forecaster said that there was 20 to 30 knot winds associated with this system, which is quite strong for a disturbance. And I think at this time, it was likely a tropical system. And as you can see, there's the wording possible tropical cyclone in the forecast for both current and 24-hour forecast. And the reason they have this wording is because this system had a medium probability to develop. And that's when they start to use the wording possible tropical cyclone. It's when there's a medium chance to develop. And this is the tropical weather outlook that was given by the forecaster at the time. And this system, they didn't issue advisories for this system because I'm assuming it's because they didn't think it was worth it. The system was going to dissipate within 12 to 24 hours. I think it was just such a short, brief time that the forecaster didn't think it was worth the time to put out advisories for it. So in summary, a variety of data sets were used to try and discover the missing storms in the East Pacific. The goal is to make sure that the National Hurricane Center database is up to date, and I think it is for 2019 to 2000. But only 3 disturbances were analyzed from 2019 to 2000. Only one of these was found to be a potential tropical cyclone. And this was honestly like looking for a needle in a haystack. It was very, very hard to find good candidates to analyze. I mean, your preseason tropical cyclones are already so rare in and of itself. And then you're looking for tropical cyclones that were undetected by some of the best tropical meteorologists in the country. So it's really hard to find any. And there are likely many missing storms from the East Pacific past the year 2000 because the lack of instrumentation and tools causes there to be more missed storms as the further back you go in time. And my next steps, I have to wait for the National Hurricane Center Best Track Committee to confirm or deny if this disturbance was a tropical cyclone. So at the end of the season, they go and they will decide if my results show that this was a tropical cyclone. So I think it'll be sometime at the end of November or December when I will find out. And then besides that, I plan to apply to graduate schools with a focus in tropical meteorology. I'm still not sure what schools I want to apply to, but I do know I want to focus on tropical meteorology. And after I get my master's degree, I hope to get a job at a National Weather Service office after graduate school, and possibly even the National Hurricane Center one day. And acknowledgements, I want to thank the National Center for Environmental Information. They provided the satellite imagery for me. I want to thank Nestis for providing the scatterometer data. It was very useful for my project. And then I want to thank the National Hurricane Center and the Tropical Analysis and Forecast Branch for providing high seas forecasts, the graphical tropical weather outlooks, and the surface analysis data. And then I want to give a special thanks to Dr. Christopher Lancy for helping me throughout the summer and answering the hundreds of questions that I gave him. And then I want to thank Dan Mundell for giving us the Dvorak classifications for all of the disturbances that we looked into. I really wish I could have showed you guys all 3 disturbances, but I didn't think I had the time to go into detail with all 3 disturbances. And then I want to thank the Hollings Scholarship Program for giving me this opportunity.